Something is happening right now that should not be possible. Electrons are walking through walls, not through holes, not around the edges, through the wall itself. No door, no break, no gap, just gone from one side and appearing on the other. Scientists measure it. Engineers build chips that depend on it. The sun runs on it. Your DNA repairs itself because of it. And for about 100 years, the smartest people alive have been unable to explain why the universe allows this at all. Quantum tunneling is not a theory anymore. It is a measured, tested, photographed fact. And when you understand exactly how it works, and how many things in your daily life depend on particles breaking the rules, the world looks completely different. This is every absurd tunneling trick that defies solid walls explained. Let us start with what a wall actually is. Not a philosophical wall, a physical one. You press your hand against a table and it does not go through. That feels obvious. But the reason it stops is not because the table is solid in the way you picture solid. The atoms inside that table are almost entirely empty space. If you took the nucleus of a hydrogen atom and made it the size of a baseball, the electron orbiting it would be roughly 2 kilometers away. Everything between them, empty. The wall you touch is, in terms of actual matter, almost nothing. What stops your hand is electrical repulsion. The electrons on the surface of your skin push against the electrons on the surface of the table, like charges repelling each other. The wall is not a wall of matter, it is a wall of force. That wall of force is what physicists call a potential energy barrier. It is a region where the energy required to pass through is higher than the energy the particle actually has. Classically, in the world of Newton and common sense, that means the particle cannot pass. If you throw a ball at a hill and the ball does not have enough energy to reach the top, it rolls back down, every time, no exceptions. The barrier is real, and the particle obeys it. For 200 years, that was physics. The rules were clean. Then the 20th century arrived and broke everything. In 1923, a French physicist named Louis de Broglie proposed something wild. He said particles are not just particles. They also behave like waves. He got his doctorate. His advisor thought the idea was so strange that he sent a copy to Albert Einstein to make sure the student was not insane. Einstein said the idea was correct. 3 years later, in 1926, Erwin Schrödinger wrote the equation that describes exactly how these particle waves behave. The Schrödinger equation is one of the most important equations in all of science. It tells you the probability of finding a particle at any given location. And when you apply it to a barrier, something strange falls out of the math. The probability does not drop to 0 on the other side. It drops. It drops hard, but it does not reach 0. There's always a small tail of probability leaking through. Always. The particle does not need enough energy to climb the wall. It can appear on the other side, because the math says it can be there. Schrödinger himself was reportedly uncomfortable with some of the implications of his own equation. He spent years arguing with Niels Bohr and Werner Heisenberg about what the wave function actually meant physically. The debate, called the measurement problem, has never been fully resolved. But regardless of what the wave function means philosophically, it predicts outcomes with extraordinary precision. And one of those outcomes, written clearly into the mathematics, is that particles can cross barriers they classically cannot cross. The equation does not hedge. The math is not ambiguous. The tail exists. The probability leaks, always. This is not a metaphor. Physicists tested it. In 1927, Clinton Davison and Lester Germer at Bell Labs in New Jersey fired electrons at a nickel crystal and watched them diffract, exactly the way waves do, particles behaving as waves. Confirmed. The wave nature is real, and if the wave nature is real, the tunneling probability is real. By the early 1930s, George Gamow, a Ukrainian-American physicist, had already used tunneling to explain radioactive decay. He was 24 years old when he wrote the paper. The nucleus of a radioactive atom contains particles called alpha particles. Those particles are trapped inside a barrier created by the nuclear force. Classically, they should never escape. The barrier is too high, but they do escape, and Gamow showed that tunneling is exactly why. The alpha particle does not climb over the barrier. It appears on the other side. Gamow's calculation matched the observed decay rates of dozens of radioactive elements. The math worked. If you value documented science history like this, subscribe. It is the best way to support the work. Also comment what city you're hearing this from. This script is researched and factual, drawing from sources including the Physical Review Letters Archive going back to 1913, and Richard Feynman's lectures on physics delivered at Caltech between 1961 and 1963, which remain some of the most precise, plain language explanations of quantum mechanics ever recorded. Now back to the information. So tunneling is real. How real? Here is a number that will help you understand the scale. The tunneling probability depends on 3 things: the mass of the particle, the width of the barrier, and the height of the barrier. For an electron hitting a barrier 1 nanometer wide, which is about 10 hydrogen atoms lined up, the tunneling probability can be as high as 1 in 10 to the power of 4. That means roughly 1 in 10,000 electrons makes it through. That sounds small, but electrons move fast, and there are an almost uncountable number of them, and 1 in 10,000 is not zero. For a heavier particle, the probability collapses fast. A proton is about 1,836 times heavier than an electron. That extra mass, according to the Schrödinger equation, makes the tunneling probability drop by a factor so large it would take several lines to write the number. A golf ball tunneling through a wall has a probability so small it would require more attempts than there are atoms in the observable universe before it happened once. This is why you do not fall through floors. It is also why electrons do what they do. Now here is the first absurd trick. The tunnel diode, invented in 1957 by Leo Esaki, a Japanese physicist working at Tokyo Tsushin Kogyo, which would later become Sony. Esaki was 23 years old. He built a semiconductor device so thin that electrons could tunnel through it, and he measured the current, not estimated it, measured it. The device did something no classical component could do. As the voltage increased, the current first went up, then went down, then went up again. That negative resistance region, where more voltage meant less current, was caused entirely by tunneling. The tunnel diode was faster than any transistor at the time because it did not require electrons to actually travel through the material. They arrived on the other side before most components had finished deciding what to do. Esaki won the Nobel Prize in Physics in 1973. The citation specifically named the experimental discovery of tunneling in semiconductors. This was not theoretical. This was a device you could hold. The tunnel diode opened a door, and what walked through that door changed the world in ways most people never trace back to the source. Before the tunnel diode, high-frequency electronics required bulky vacuum tubes or relatively slow transistors. The tunnel diode could switch at frequencies that were, for its time, practically unimaginable. Early applications included microwave oscillators and amplifiers used in radar and satellite communication. The device was compact, rugged, and operated on a quantum effect so counterintuitive that engineers initially argued about whether it was real or an artifact of measurement error. Esaki's response to those engineers, years later, was to hold up his Nobel Prize certificate. The argument ended. Every modern computer chip depends on a device called a transistor. A transistor is essentially a gate. It lets current flow or stops it, representing a 1 or a 0. In the early days of computing, transistors were large. The first transistors in the late 1940s were about the size of the tip of your thumb. By the 1970s, the process of miniaturization had begun in earnest. Gordon Moore, one of the founders of Intel, noticed in 1965 that the number of transistors on a chip was doubling roughly every 2 years. That observation became Moore's law, and for decades it held. But as transistors got smaller, something began to happen that engineers did not fully anticipate. The barriers inside them got thin enough for electrons to tunnel through when they were not supposed to. By the time transistors reached sizes measured in single-digit nanometers, the problem became impossible to ignore. At 5 nanometers, the gate oxide layer inside a transistor, the insulating layer that is supposed to block current flow when the transistor is off, is thin enough for quantum tunneling to punch right through it. Electrons leak even when the gate says stop. This is called gate leakage current. It wastes power, it generates heat. It is one of the fundamental physical limits that makes chip design at these scales so difficult. As of 2023, the most advanced chips from companies like TSMC and Hsinchu, Taiwan, are manufactured at a 3 nanometer process node. At those scales, the gate oxide layers are roughly 5 atoms thick, 5 atoms. Quantum tunneling is not an edge case anymore. It is a central challenge that every chip architect in the world is designing around right now. Some approaches try to use alternative materials with higher barriers, like hafnium oxide instead of silicon dioxide, to reduce leakage. Others use entirely different transistor geometries, like FinFETs and GAA transistors, to better control the channel and reduce tunneling paths. But the tunneling is still there. The wave function leaks. The physics does not care about the engineering deadline. Here's the second absurd trick. The scanning tunneling microscope, invented in 1981 by Gerd Binnig and Heinrich Rohrer at IBM's Zurich Research Laboratory in Switzerland. They won the Nobel Prize in Physics in 1986, just 5 years after the invention, which is extraordinarily fast for a Nobel. The device works like this. You take a metal tip and sharpen it until the very end is a single atom. You bring that tip to within about 1 nanometer of a conducting surface. You do not touch the surface, you hover just above it. Then you apply a small voltage between the tip and the surface. Classically, no current should flow. There is a gap of vacuum between them and the electrons have no path to cross it. But because the gap is so small, electrons can tunnel across the vacuum. A measurable current flows. Here is the remarkable part. That current is extraordinarily sensitive to the exact distance between the tip and the surface. Change the gap by a single atom, and the current can drop by a factor of 10. A factor of 10 for 1 atom of distance. This sensitivity is what makes the device revolutionary. You scan the tip across the surface, keeping the current constant by adjusting the height of the tip, and you trace out the surface atom by atom. You can see individual atoms, not approximate them, not infer them, see them. In 1989, Don Eigler and Erhard Schweitzer at IBM's Almaden Research Center in California used a scanning tunneling microscope to position 35 xenon atoms on a nickel surface. They spelled out the letters IBM. It was the first time in history that human beings had deliberately arranged individual atoms. The tool that let them do it was built entirely on quantum tunneling. Subscribe if you want more documented science history. Comment your city. Back to the story. The tunnel diode opened the first door. The scanning tunneling microscope opened the second. Invented in 1981 by Gerd Binnig and Heinrich Rohrer at IBM's Zurich Research Laboratory in Switzerland. They won the Nobel Prize in Physics in 1986, just 5 years after the invention, which is extraordinarily fast for a Nobel. The device works like this. You take a metal tip and sharpen it until the very end is a single atom. You bring that tip to within about 1 nanometer of a conducting surface. You do not touch the surface, you hover just above it. Then you apply a small voltage between the tip and the surface. Classically, no current should flow. There is a gap of vacuum between them and the electrons have no path to cross it. But because the gap is so small, electrons can tunnel across the vacuum. A measurable current flows. Here is the remarkable part. That current is extraordinarily sensitive to the exact distance between the tip and the surface. Change the gap by a single atom, and the current can drop by a factor of 10. A factor of 10 for 1 atom of distance. This sensitivity is what makes the device revolutionary. You scan the tip across the surface, keeping the current constant by adjusting the height of the tip, and you trace out the surface atom by atom. You can see individual atoms, not approximate them, not infer them, see them. In 1989, Don Eigler and Erhard Schweitzer at IBM's Almaden Research Center in California used a scanning tunneling microscope to position 35 xenon atoms on a nickel surface. They spelled out the letters IBM. It was the first time in history that human beings had deliberately arranged individual atoms. The tool that let them do it was built entirely on quantum tunneling. The image was published in the April 5th, 1990 issue of the journal Nature. It is 9 nanometers wide, 9 billionths of a meter. In that space, 3 letters, arranged by human intention, 1 atom at a time, held in place by quantum forces so small they defy everyday description. The sun generates energy through nuclear fusion. Hydrogen nuclei, which are single protons, smash together under enormous pressure and heat in the core and fuse to form helium, releasing energy in the process. That much most people know. What most people do not know is that the sun is not nearly hot enough to do this. Not classically. The core of the sun is approximately 15 million degrees Celsius. 15 million? That sounds impossibly hot. But to overcome the electromagnetic repulsion between 2 protons and get them close enough to fuse, you need temperatures closer to 10 billion degrees. The sun's core is about 667 times too cold. Every physicist who calculated this in the 1920s hit the same wall. The numbers did not work. The sun should not be able to fuse hydrogen at its actual temperature. And yet, there it is, shining. For approximately 4.5 billion years already, and expected to continue for roughly another 5 billion. The answer, once again, is tunneling. Protons in the solar core are not classical particles. They are quantum particles. They have wave functions. And even though the average proton does not have enough energy to climb the repulsion barrier, its wave function has a non-zero probability of appearing on the other side. At 15 million degrees, that probability is small. Very small. One calculation puts the probability of any given pair of protons fusing on any given close approach at roughly 1 in 10 to the power of 28. That is an almost absurdly tiny number, but the sun contains approximately 2 times 10 to the power of 57 protons. And they are colliding constantly. The numbers multiply out. About 600 million tons of hydrogen fuse every single second in the solar core. Not because any individual proton easily breaks through the barrier, but because there are so many protons making so many attempts that even a vanishingly small probability adds up to a star's worth of power. 4.5 billion years of sunlight, produced by quantum rule breaking on an astronomical scale. Every photon of light that ever touched your skin came from a fusion event in the sun's core that began with a tunneling probability of 1 in 10 to the power of 28. The warmth you feel on a summer afternoon is the accumulated result of quadrillions of quantum dice rolls, each individually almost certain to fail, but collectively producing the most important ongoing event in the solar system. This was confirmed theoretically by Hans Bethe, a German-American physicist working at Cornell University, who published his detailed description of the solar fusion chain in 1939. Bethe won the Nobel Prize in Physics in 1967, specifically for this work. His calculations for the proton-proton chain reaction, which is the dominant fusion pathway in the sun, have been tested against solar neutrino measurements for decades. The numbers match. Tunneling runs the sun. Now the third absurd trick: enzymes and the chemistry of life. Inside every living cell, chemical reactions happen that should not happen at room temperature. A chemical reaction requires molecules to get close enough to rearrange their electrons. There is an activation energy barrier for every reaction, a threshold the molecules must cross. For many reactions, critical to life, the classical activation energy is too high for room temperature to supply. And yet, the reactions happen. Enzymes are proteins that help catalyze reactions by lowering the activation energy. And for about 60 years, biochemists assumed that explained everything. Then experiments began to show something odd. Some enzyme-catalyzed reactions, particularly those involving the transfer of hydrogen atoms, were happening far faster than classical models predicted, and the rate did not drop the way it should as temperature decreased. A classical particle slows down as it cools. A tunneling particle's probability depends mostly on barrier shape and width, not temperature. When researchers cooled enzyme reactions and the rate held up better than expected, tunneling was the explanation. The enzyme alcohol dehydrogenase, which is the protein responsible for breaking down alcohol in your liver, was studied extensively by Nigel Scrutton's group at the University of Manchester in the United Kingdom. A paper published in 2006 in the Proceedings of the National Academy of Sciences showed kinetic isotope effects in the enzyme that could only be explained by quantum tunneling of hydrogen atoms. When you drink alcohol and your liver processes it, hydrogen atoms are tunneling through quantum barriers inside the enzyme. This is happening right now in billions of human bodies. Not in a laboratory, not in a particle accelerator, in the most ordinary biological process that happens after a glass of wine. DNA also depends on tunneling. The base pairs of DNA are held together by hydrogen bonds. Protons in those bonds can occasionally tunnel from one position to another, a phenomenon called proton tunneling. When they do, they can create what are called tautomeric forms of the DNA bases, slightly altered versions that can pair with the wrong partner during replication. This was first proposed by Per-Olof Lövden, a Swedish physicist, in 1963. The idea was that some fraction of spontaneous genetic mutations, the random errors that drive evolution, might be caused by quantum tunneling of protons inside the double helix. Modern research has taken this further. A study published in the journal Chemical Science in 2022 by researchers at the University of Surrey, the University of Leeds, and University College London used quantum mechanical calculations to show that proton tunneling in DNA-based pairs could produce mutation-inducing tautomers at biologically relevant rates. Quantum tunneling may be one of the engines of evolution. The random dice that mutation represents might be quantum dice, the deepest randomness in biology reaching back to the deepest randomness in physics. The fourth absurd trick is one that astronomers call hydrogen line emission, and physicists call a forbidden transition, and it is responsible for mapping the entire galaxy. In 1944, a Dutch astronomer named Hendrik van der Holst predicted that neutral hydrogen atoms scattered through space should occasionally emit radiation at a specific wavelength of 21 centimeters. The emission happens when the spin of the electron in a hydrogen atom flips from being aligned with the proton to being anti-aligned, releasing a tiny amount of energy as a radio wave. Van der Holst called this a forbidden transition because, under the rules of quantum mechanics as they were understood then, the probability of it happening spontaneously was extremely low. Extremely low, in this context, means the average hydrogen atom in deep space takes about 11 million years to emit that photon, 11 million years per atom. But space is full of hydrogen atoms, enormous clouds of them drifting between stars, and radio waves travel freely through dust and gas that blocks visible light. In 1951, Harold Ewan and Edward Purcell at Harvard University in Cambridge, Massachusetts, detected the 21-centimeter line for the first time, using a horn antenna mounted on the roof of a physics building. The detection confirmed Van der Holst's prediction. And once radio astronomers began mapping the sky at 21 centimeters, they could trace the spiral arms of the Milky Way for the first time. The structure of our galaxy, the map of where we live in the universe, was drawn using emissions from individual tunneling events happening in hydrogen atoms at a rate of once every 11 million years. Summed across enough atoms, it becomes the loudest signal in the radio sky. Quantum tunneling also makes it possible to store your music, your photographs, and your documents. Flash memory, which is the storage technology inside every smartphone, every USB drive, and every solid-state hard drive on Earth, works by trapping electrons behind a quantum barrier. The memory cell in flash storage contains what is called a floating gate, a tiny conductor completely surrounded by insulating material. To write data to the cell, a voltage is applied that forces electrons to tunnel through the insulating layer and into the floating gate. Once there, they are trapped. The insulating barrier prevents them from tunneling back out under normal conditions. To erase the data, a larger voltage is applied in the opposite direction, and the electrons tunnel back out. The data is represented by whether electrons are present in the floating gate or not. 1 is electrons in, 0 is electrons out. Every single bit stored on every flash memory device in the world is held in place by quantum tunneling. When a flash drive begins to fail after many write and erase cycles, it is partly because the insulating layer degrades from the repeated tunneling stress and begins to leak. The electrons that were supposed to stay put start tunneling through when they are not supposed to. Data corruption at the quantum scale. The global flash memory market was valued at approximately $80 billion in 2023. Every single device in that market stores information through a process that 60 years ago would have been described as electrons, magically crossing a wall they cannot cross. The entire digital economy, every photograph, every message, every financial record stored on solid-state media is preserved by quantum tunneling. The universe's rule-breaking is the thing keeping your memories intact. The fifth absurd trick involves the night vision of birds. This one is stranger than the others. Birds migrate. Many species navigate over thousands of kilometers with precision that has no obvious explanation. Homing pigeons, bar-tailed godwits crossing from Alaska to New Zealand in 8 days, European robins navigating across entire continents in darkness. For decades, the magnetic sense of birds was suspected but poorly understood. Then researchers found cryptochrome proteins in the eyes of birds, like the European robin. These proteins are light-sensitive and located in the retina. In 2008, researchers including Henrik Moritzen at the University of Oldenburg in Germany began showing that the magnetic compass of birds depended on the eyes, not on iron mineral deposits in the beak, as had been assumed. The cryptochrome hypothesis, developed extensively by Klaus Schulten at the University of Illinois at Urbana-Champaign from the 1970s through the 2000s, proposes a specific mechanism involving what is called a radical pair. Here's how it works. Light hits a cryptochrome molecule in the bird's eye. A single electron tunnels from one part of the molecule to another, a distance of about 1.5 nanometers, creating 2 unpaired electrons. These 2 electrons are entangled. Their quantum spins are linked. The Earth's magnetic field is too weak by any classical measure to have any chemical effect on biology. The field strength at the Earth's surface is about 50 microtesla. Ordinary chemical bonds are not affected by fields that weak, but an entangled radical pair is different. The magnetic field influences the spin state of the entangled electrons, and whether they end up with parallel or anti-parallel spins determines which chemical pathway the reaction takes. The bird's visual system may be reading this signal, essentially seeing the Earth's magnetic field as a pattern overlaid on its vision, a map of magnetic information invisible to human eyes but navigational for the bird. This is a system built on quantum entanglement triggered by quantum tunneling, operating inside a living animal's eye, directing one of the great navigational feats on Earth. The research is ongoing and contested in its details, but the tunneling step in cryptochrome activation is well established. A paper in the journal Nature Communications from 2021 by researchers at the University of Oldenburg confirmed that disrupting the cryptochrome pathway disrupted magnetic sensing in European robins. The sixth absurd trick is perhaps the most unsettling. It is called quantum tunneling time, and nobody fully agrees on the answer yet. When a particle tunnels through a barrier, how long does it take? The question sounds simple. The answer has caused arguments among physicists for 60 years. In 1932, Leonid Mandelstam and Mikhail Leontovich in Moscow first raised the question. For most of the 20th century, various theoretical answers were proposed. Some suggested the tunneling time was finite and measurable. Others, including calculations by Eugene Wigner, suggested the transit could happen faster than if the barrier were not there at all, potentially faster than the speed of light would allow. This is called the Hartmann effect, named after Thomas Hartmann, who described it in a 1962 paper in the Journal of Applied Physics. The Hartmann effect says that for thick enough barriers, the tunneling time becomes independent of barrier width. Add more barrier, and the particle gets through in the same time, as if it is skipping the inside of the barrier entirely. This raised obvious and alarming questions about whether tunneling could be used to send information faster than light, which would violate special relativity. The consensus answer, which took decades to build, is that it cannot. The tunneling probability drops so fast with barrier thickness that while the apparent transit time is strange, you cannot use it to send a signal. The particle arrives quickly, but you cannot control which particles tunnel and which do not, so you cannot encode a message in the timing. But the tunneling time question remained experimentally unanswered for a long time. In 2020, a group at the University of Toronto, led by Ephraim Steinberg, published a paper in Nature measuring the tunneling time for rubidium atoms, tunneling through a laser barrier. Using a technique called Larmor precession, where a weak magnetic field causes the spin of the atom to rotate at a known rate, so the spin acts as a tiny clock, they measured how long the atom spent inside the barrier. Their result, the atom spent approximately 0.6 milliseconds inside the barrier, which was less time than a free atom traveling the same distance in empty space would have taken. The atom appeared, by this measure, to traverse the barrier region faster than it could have if the barrier were not there, faster than free flight. The physicists were careful to note that this does not mean faster than light and does not allow signaling, but it does mean the particle's experience of time inside the barrier is genuinely, measurably strange. The physics inside a barrier is not the same as the physics outside it. The particle is doing something in there that classical time does not describe. The seventh absurd trick is the field emission of electrons and the technology it enabled. Field emission is a specific form of tunneling where a strong electric field applied to a metal surface pulls electrons through the surface barrier and into vacuum. Without tunneling, you would need to heat the metal to enormous temperatures to boil off electrons. That is called thermionic emission, and it is what vacuum tubes used. With field emission, you apply a strong enough electric field and electrons tunnel out at room temperature. The theory was worked out by Ralph Fowler and Lothar Nordheim in a 1928 paper in the Proceedings of the Royal Society of London, one of the first successful quantum mechanical calculations applied to a real metal vacuum interface. Field emission is the operating principle behind field emission displays, which were a type of flat panel display developed in the 1990s and 2000s. It is also behind the field emission guns used in modern electron microscopes. A field emission gun produces a beam of electrons with extraordinary coherence and brightness, far better than thermionic sources, because the electrons emerge from a nearly atomically sharp tip through tunneling. The result is electron microscope images of stunning resolution, images of individual atoms and materials, defects in crystal structures, the shapes of proteins and viruses. The biological images that helped researchers understand the structure of COVID-19, the coronavirus that caused a global pandemic beginning in 2019, were captured using electron microscopes whose electron sources operate on quantum tunneling. The map of a virus that infected billions of people was drawn with a tool built on electrons walking through walls, now a number that ties it all together. The semiconductor industry generates revenue in the range of approximately $600 billion per year as of 2023. Every chip in that industry, every transistor and every processor and memory device and communication chip operates in a regime where quantum tunneling is a dominant physical consideration. The tunnel diode that Leo Esaki built at age 23 in 1957 did not stay in the laboratory. It became the foundation of a technology stack that now underpins global computing, communication, medical devices, navigation, entertainment, and scientific research. Esaki once said in a 1973 interview that he had been told by senior engineers that what he was measuring could not be real because it violated the rules. He kept measuring. The rules were wrong. The rules have been wrong a lot. Every entry in this list represents a moment when the physical world did something that common sense said was impossible, and then researchers measured it anyway, and then engineers found ways to make money from it, and then everyone forgot how strange it was. Electrons appear on the other side of barriers they do not have enough energy to cross. Protons in the sun fuse at temperatures 667 times too low. Hydrogen atoms in your liver tunnel during alcohol metabolism. Enzymes catalyze DNA processes through quantum shortcuts. Birds read magnetic fields using entangled electrons. Stored data is held by trapped particles perched on the edge of leaking through a quantum wall. And somewhere in your eye, at this exact moment, electrons are tunneling inside proteins that handle the first steps of the chemical process that lets you see. None of this is comfortable knowledge. It does not fit the world the way common sense built it. The wave function is not located. The particle is not somewhere definite until you measure it. And the measuring is, at some level, not fully understood even today. The Copenhagen interpretation says, do not ask what the particle is doing inside the barrier. The many worlds interpretation says, every tunneling event branches reality. The pilot wave theory says there is a real trajectory, but it is guided by a wave that has no classical analog. In 2023, none of these interpretations has been experimentally ruled out. The equations work, the predictions are confirmed, the mechanism is debated. What is not debated is the outcome. In 1926, Schrödinger wrote equations on paper and tunneling fell out of the math. In 1930, Gamow used those equations to explain why uranium decays. In 1951, a radio astronomer climbed onto a roof in Cambridge, Massachusetts, and heard hydrogen atoms tunneling in deep space. In 1957, a 23-year-old in Tokyo measured electrons punching through a barrier they had no business crossing. In 1981, two physicists in Zurich suspended a single atom tip 1 nanometer above a surface and counted the tunneling electrons to trace individual atoms. In 2006, Enzymes in a university laboratory in Manchester were shown to be using the same trick that powers the sun. In 2020, physicists in Toronto measured how long a particle spends inside a barrier it is supposedly forbidden from entering, and found the answer was stranger than anything classical time could explain. The wall is not a wall. It never was. The solid seeming edge of a material is a probability that collapses from one side to the other in a gradient, not a line. There's always a tail. There's always a small chance the particle is already on the other side. That small chance is why the sun burns. It is why your chips compute. It is why birds know where south is in November. It is why your body processes alcohol. It is why the galaxy was mapped. In the IBM Almaden Laboratory on March 15, 1989, Don Eigler arranged those 35 xenon atoms into 3 letters using a scanning tunneling microscope. He moved atoms one at a time by adjusting the tunneling current to pick one up and set it down. The device that could do this had not existed 8 years earlier. The phenomenon that made the device work had not been mathematically described 60 years before that. And the particles being moved had been doing it naturally, tunneling through barriers in matter and space for as long as matter has existed. The wall was always permeable. Physics just needed long enough to admit it. The letters spelled IBM. The atoms were already on the other side before anyone asked how they got there.